the same time if this is all right with everyone. Okay. Now the yes. So the recording of last Saturday's meeting will be online tomorrow. If it doesn't appear online, please let me know. Okay. Now, well, today we'll start talking about parametrices, which is the plural of parametrics. We'll see what it is. Let's recall that to smooth complex vector bundles we can associate the spaces W which philosophically are spaces of sections such that sufficiently many derivatives are L2 integrable. A more formal definition is can be given in several ways. We've seen one definition which involves local charts, and another one which gives an equivalent metric. We could just we could take smooth sections and then choose a finite family of operators of order less than or equal s, and then take the sum of the L2 norms of this operator applied to the sections. And well, for example, although this is not a compact manifold, if x is Rn, then I want to consider only compactly supported sections. But in this case, I could take just the partial derivatives with respect to coordinates in Rn. Anyway, so we have these sections. Now, I want to define an abstract space of operators of order m. And by the way, so far everything works over R as well, but we want to use C because well, if we work over C, then there are formulas for the Fourier transform which make life easier and so on. But so far, everything can be adapted to work over R. But later on, we'll see some of the remaining parts of the theory are tricky, and this is related to the fact that the complex K theory is much easier than not much easier, but well, shall we say 4 times as easy as the real K theory. Anyway, C-linear maps. S inside Z. Okay, just C linear maps which extend continuously to all Sobolev spaces. Not necessarily differential operators, but these include and by the way, here M doesn't need to be positive, and in fact it doesn't need to be an integer. Although we'll be only interested in we'll only be interested in the case when M is an integer.
If the S minus M.
Yes, S minus M. So S is S corresponds to the smoothness of sections, and well, it stands to reason that a differential operator of order M decreases smoothness by M, hence minus M. Okay, now. Between these two spaces, there is a third one. Which is the space of pseudo differential operators. I will not I will not define those just yet. First, let's see why we need to consider those. I'll explain I'll explain what it says here. Well, let's recall that we have the cotangent bundle, which is defined in the usual way, and well, let's remove the zero section. And we get something which is homotype equivalent to the spherization of the cotangent bundle, and we denote the projection P. Okay, now what is homogeneous of degree something? Well, this means that here we have an S, which is an element of Hom P upper star, and I don't want zero. So homogeneous of order M means that for all positive T, we have this this equality. Now. For each x and psi in the tangent bundle or cotangent bundle, S gives me a map from EX to FX, but this map may depend on psi, and it often does. And homogeneous means the dependence is homogeneous in psi, meaning if we multiply psi by some positive number, we get a factor of this number to the mth. It follows straight from the definition of the symbol that the symbol of every differential of every genuine differential operator of order m belongs to this space. But in general, it's not true that every element of the space is the symbol of a differential operator. Which is why we need to extend the class of operators. Okay, now, are there any questions? Okay, before we get into the gory details of pseudo-differential operators, let's see how they help to solve differential equations. We don't know yet what pseudo-differential operators are. But, let's state some of the properties of those operators. So there exists a symbol map from BDIF blah 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 symb. And this map is surjective. So for every symbol there is an operator, which is a good thing. Which is a good thing to know, and the kernel is an operator of order 1 less. More precisely, the kernel consists of operators of order m-1. Okay, now okay, so this theorem is actually all we need to know about pseudo-differential operators in order to prove the well, the basic properties of elliptic, this time differential operators without the pseudo. And let's start with this. Let's say that we have a genuine elliptic operator from E to F. Then there exists a pseudo differential operator of order minus m, such that the compositions are almost equal to the identity operators, almost up to an element of op minus 1. We'll see in a minute why this implies that this thing is almost zero.
I think this operator is from E to E.
Let's see. Oh yeah. Thank you. This one is from E to E, and the other one. Is from F to F. Okay, well, this this property is more or less straightforward if we assume that the symbol of the composition of two pseudo differential operators is the composition of the symbols. Since the symbol is since the operator is elliptic, we can invert the symbol. This time we just use the fact that when we defined an elliptic operator, we required that the map S from here to here should be invertible for every element of the cotangent bundle minus 0. So there is an inverse. Well, let's invert it.
What to do with 0?
Nothing. It's we just leave it alone. Okay, so S minus 1 is in fact inside the space sim minus m, which is very very straightforward. If I have a family of invertible maps which depends homogeneously on some parameter, in our case psi, and the family of the inverses is also homogeneous of degree minus the degree of s. Does this make sense, Volodya? Well, we have this. For every x and psi, we have an isomorphism between Ex and Fx, but this isomorphism also depends on psi. Now, how does it depend on psi? Well, it depends in a homogeneous way, which means if we multiply psi by positive real number t, the map gets multiplied by t to the m. I have such a family. Now I want to, but I also assume that all these maps are isomorphisms. So I can also consider the family of the inverses, which will go from fx to ex. And my claim is the family of the inverses is also homogeneous in psi of degree minus m. Okay, so we'll get a minus m here. And we construct a pseudo differential operator with symbol s to the minus 1, and then I calculate the zeroth symbol of both sides. And I use this formula, and I get 0. I think it's it's clear because I get the identity minus identity, which is 0. Okay, is this part? Does this part make sense? Okay, now it works. It works in the same way for the other composition. So So we get this difference, which is an operator of degree -1, of order -1. Well, let's recall what operators of order -1 are. Well, these, by definition, these are maps from sections to sections, which extend a continuous map from W to W+1. Well, Well, W+1 is WS+1 is inside WS, and so in particular we also get an extension from of the operator to an operator from WS to WS, and this operator is compact by the Relic lemma. Now, is this part clear to everyone, or should I explain it in more detail? What does the Relic lemma say? The Relic lemma says that the inclusion of WS+1 into WS is compact. Okay, I'll erase this part. Does everyone remember what a compact operator is? The image of the unit ball has compact closure. And by the way, I've forgotten to say what parametrices are. an operator such that we have these two compositions minus the corresponding identity maps of order -1 are called Barrow matrices. The same D could have several Barrow matrices. Okay, now let's let's remember that we're actually more interested in smooth solutions and smooth sections than in Sobolev spaces. Sobolev spaces are just a tool. So let's see another application of all this. But before we do, I will state a lemma from functional analysis, which we will prove later. And this lemma is probably familiar, or maybe not. But anyway, let me write the lemma first. Okay, okay, let me use the letter S, and let me also assume that the map is compact. So suppose we have a compact operator between two Banach spaces. Then I don't want to have two Banach spaces because I want to have the identity map here. So it doesn't work. Doesn't work for two, but it works for one. So let's say that the source space and the target space are the same. Okay, now let's erase complementable. I'm not sure about that. Could be true, could be false. Well, For Hilbert spaces, all closed subspaces are complementable. In general, I only claim that the image is of finite codimension and it's closed. But in the Hilbert case, every closed subspace is complementable. Anyway, let's see. Okay, does everyone know what a Banach space is? Probably yes. Now, has anyone taken the functional analysis course?
One semester.
Say again?
One semester.
1 semester. Okay, was this did the course mention this result? Okay. Anyway, we're okay. Let's assume this result, and we'll. Has anyone seen this theorem anywhere at all? Well, they normally mention Fredholm operators in the functional analysis course, and this is probably one of the theorems which people normally prove when they talk about Fredholm operators. But anyway, never mind that. Let's first see some applications, and then we'll prove this theorem later. Okay, so we did see one application. Let's prove another one. Well, let's prove the regularity theorem for elliptic operators. Well, before we prove the theorem, what's going on there? Hey. Before we prove the theorem, what does the theorem say? Well, let's see. So we'll start with an elliptic operator. Well, we know that this operator extends to all Sobolev spaces. Well, let's call the extension ds. Okay, so let me. Okay, so suppose I have a section psi of the bundle F such that no, suppose I have a psi a section of F, and eta is so psi is smooth, but suppose I also have a section eta which is not necessarily smooth. Which in fact belongs to this to the Sobolev space. And such that the operator D, or more precisely its extension, takes eta to psi. Then my claim is that eta is also smooth. Well, what do? I use the parametrics. Or more precisely, I use a parametrics. It doesn't matter which one, as long as it is one. What do I want to do? I want to increase the smoothness by 1. The smoothness of what? The smoothness of eta. Okay, so what do I have? I have, well, ds.
Shouldn't E be in another direction?
Oh yes, thank you. From F to E. Okay, so I have okay, now I have this identity. And now P still takes smooth sections to smooth sections. So let me apply this this identity to eta. So I know that d of eta is psi, which is smooth. So this thing is smooth. Well, let me call this whole thing S. I know that S of eta belongs to Ws plus 1. To Ws plus 1 of what? Of E. Okay, so I've taken eta inside Ws, and I've shown that eta is in fact inside Ws plus 1. So I've increased the smoothness by 1. And then I can repeat the same strategy, increase smoothness again, and then again, and so on, and finally the conclusion is that eta is in fact inside the intersection of all Sobolev spaces, and this is the same as C infinity by Sobolev's lemma. Well, let's try to understand it. So we have two sections. One is smooth, the other one is not necessarily smooth, and we want to prove that we want to prove that it is. I take the parametrics. Well, we know that it's an operator of Wood minus m, so it has extensions to all Sobolev spaces, we have this identity because that's how we define parametrices.
Why there is S minus M under?
Well, because this one goes from WS to WS minus M, and this one goes from WS minus M to back to WS. Well, what's important is that the whole thing has order -1. So it takes eta to an element of W s plus 1. Okay, now so this whole thing applied to eta is inside WS plus 1. But what is this thing? This is this composition plus or minus eta itself. Okay, well, this composition is inside, in fact, C infinity. Because d of psi is smooth, and so p of d of psi is also smooth. Okay, so this is infinitely smooth, and this minus psi. Let me write it down. Oh, sorry. Yes, eta. Sorry. Yes. Yes. Sorry. Thanks. Yes, we want. Actually, I have. Anyway, I have some problems with my eyes at the moment, and as a result, I don't quite see everything I write. So, which is inconvenient. Anyway, well, it's not as bad as it sounds, but anyway. So yes, so we have this thing, which is S of eta, which is inside WS plus 1. This thing is smooth, so eta is inside WS plus 1. Well, this is the regularity theorem, and let's prove another theorem, which okay, so this was application number 2. Well, let's also do application number 3. Suppose we suppose we again have an elliptic differential operator. Now we want to prove that the kernel and co-kernel of this operator have finite dimension. This time we consider it as an operator from smooth sections to smooth sections. So you need to use Sobolev spaces in between, but the statement is about smooth sections. The kernel and co-kernel are finite dimension. Okay, now let's see. Well, what do? I use again a parametrics. Okay. Okay, so I have well, I have continuous extensions to all Sobolev spaces. Well, let's see. Well, what do we know? What do we know about this operator? Well, well, we know that there is a parametrics. That's well, which is something. Well, let's try to draw this in. So we have S minus M, F. Then we have P, S minus M. And they all go to Ws of E. Does this diagram make sense? So we don't know much about this operator yet, but we know that this operator is what is identity plus compact. Plus a compact operator. Okay, so the kernel.
Why
Well, this is one of the properties of the parametrics. Well, basically, if we apply D first and P after it, we get the identity plus a compact operator. Why compact? Because it has order -1. As an operator from WS to WS. And why does it have order -1? Well, because it extends to an operator from WS to WS plus 1. And the inclusion of S plus 1 into S is compact by the Redick lemma.
Now, I understand that I don't understand why operator of order -1 is compact.
By the Redick lemma.
It follows from Redick lemma?
Yes, because what's an operator of order -1? It's an operator which factors through the inclusion of WS plus 1 into WS. And the latter inclusion is compact. And yes, if I have a compact operator somewhere in the composition, on the left or on the right, then the whole composition is compact. Well, this diagram tells me that the kernel of this map is finite dimensional. Why? Because the kernel of this map is finite dimensional. Okay, now let's also note that all these kernels are in fact equal the kernel of D. Why? Well, we apply elliptic regularity to the zero to psi taken to be the zero section. Yegor, does this make any sense? Значит, то, что все ядра совпадают с ядром D. У меня куча операторов, там у каждого свое ядро, значит, утверждает, что на самом деле они все совпадают. Значит, а мы уже доказали, что значит, если у нас D от чего-то гладкое, то это что-то, от чего мы берем D, само гладкое. Ну, возьмем в качестве вот этого чего-то 0. 0 гладкий. Значит, поэтому значит, все элементы ядра вот этого оператора на самом деле будут гладкими, то бишь будут ядром самого оператора D. То есть будут элементами ядра самого оператора D. So we deduce that the kernel of D is finite dimensional, and here we use the fact about Banach spaces, which I mentioned earlier, and then we use elliptic regularity to prove that all kernels are in fact the same. Okay, so this was the statement for kernels. What about co-kernels? Well, we again use the parametrics. Okay, by the way, here there's a small remark. Actually, we can deduce the finite dimensionality of the kernel without using regularity. Why? Well, because we know that this is finite dimensional, that the kernel of D is certainly inside the kernel of ds. So we need elliptic regularity only to prove that all the kernels coincide. The fact that the dimension of the kernel is finite follows from just the inclusion of the kernel of D in the kernel of ds. Okay, now what about the co-kernels? Well, let's see. We compose the operators in we're going to have WS, E, WS plus M, F, ES, and then D.
E and F.
Yes, you're probably right. Yes. There should be an E, there should be an F. Okay, we draw the same diagram, but for the other composition. Okay, now. So what do we have? We have the co-kernel of ds plus m. And there is a map a surjective map from the co-kernel of this map to the co-kernel of this map. Why? Well, because the image of the upper arrow is contained in the image of the lower right arrow. And this and this arrow is again the identity plus a compact operator. So the co-kernel is finite dimensional. Okay, now let's see if we can deduce that the co-kernel of D is finite dimensional. Let's see, I think so what about the co-kernel of D? Okay, well, let's see. So my claim is that C infinity xf divided by the image of D is inside Ws F or divided by the image of ds plus m.
The image of D is the intersection of image D plus S with C infinity. By regularity.
Yes, by the regularity theorem. So here we the map from this space to this space exists by general nonsense. It's not always well. It's not. It is injective, but not for free. Why is it injective? Well, suppose we have an element here which ends up here. So an element, a smooth section, which is inside the image of some Sobolev extension. By the regularity theorem, the element inside the image of the Sobolev extension is in fact inside the image of D itself. Okay, so ds plus m of W S plus M of Ws plus M E. So this is injective by regularity. Okay, are there any questions? Well, I think we've run over time, if there aren't any questions, then my suggestion is let's stop here, and then after the break we'll change the subject completely and talk about the index formula applied to some simple operators. So we'll start, we haven't actually calculated the index of anything using the index formula. And it's about time we did that. So we'll do that after the break. Well, yes, because there's on Saturday we did talk a little about the K groups, and basically we defined a map from K theory to cohomology. This map was called the Chern character. And I mentioned, but we didn't prove, that this map is an isomorphism to prove it's an isomorphism, one needs some information about K groups, namely these are the degree zero part of a cohomology theory. Okay, do we want to talk about cohomology theories in general, or do we want to see a concrete calculation of the index of some operator? Okay. For this calculation, we basically have all we need, except one thing. We need the relative K groups. Well, it says here what these are on page 2, I think. Yes. The definition is given there, so there is no point in writing it on the board. Now, let me just say that once I have two vector bundles on X and an isomorphism over Y, this gives me an element of the relative K group, and this element is 0 if the isomorphism extends to Y. Extends to an isomorphism of if the isomorphism over Y extends to an isomorphism over X.
What is the difference between calligraphic K and just normal K?
Well, let's see. Yeah. I don't know. Probably there isn't. Probably it's just a typo. And we also need the relative term character, which goes from the relative K group to the relative to the relative cohomology.
Зависит, что канон табличника обозначается, обозначает через вот это как графическое.
Где?
В последнем абзаце первой страницы.
Последний абзац, первой страницы.
Последняя формула первой страницы.
Okay. Hold on. K naught is denoted. Well, M is some monoid, and okay. Okay. I now see. I now see the difference. So K. The calligraphic K denotes the K group of the monoid of vector bundles or vector bundles plus isomorphisms of some type or another. Now for X compact, this or more precisely compact CW complex, this group coincides with homotypic classes of maps into BU. So for our purposes, there will be no difference. But for more general spaces, it still makes sense to consider vector bundles and the monoid of vector bundles. But well, for not necessarily compact spaces, this calligraphic K is hard to describe. So doesn't necessarily coincide with the set of homotypic classes of maps into BU and so on. I don't think we need to worry about this. Okay, now let's calculate the index of the Durham operator. Using the index formula. By the way, where is the index formula? Okay, well, it's on page 3, I think. Okay. Okay, so let's see. Let's start with question 2. Let's start with question 6. So we have GM tilde, which is the same as BSOM. Now, does any of this make any sense? BSO is the classifying space for the group SO. It's the same as the orienting cover, or the double cover of the Grassmannian GM of R infinity. Does this make any sense? Okay. It looks like the first sentence makes sense. Let's move on to the second sentence. We suppose that M is even and set L equal 1/2 of M. Blah, 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 blah. We'll construct a CW complex X and a map. Okay. We don't have the previous problem sheet, but I remember what was in it. Okay, first of all, what is gamma M tilde? Gamma M tilde is the universal oriented bundle of the oriented Grassmannian. Basically, this bundle has the same properties as gamma M, but for oriented bundles. Every oriented bundle is induced from gamma M tilde. Using some map, and homotypic classes of maps are one-to-one to homotypic classes of to isomorphism classes of oriented bundles. Okay, now we do what? Okay, now we want to use a version of the splitting principle. But does everyone remember what the splitting principle says for complex vector bundles? Well, first of all, the easiest version, which we saw, and we actually used it a few times. It involves complex vector bundles and integral cohomology? Well, there is a straightforward analog for real vector bundles. But this time we need to use a cohomology modulo 2. But otherwise, the rest is completely straightforward. There is a space such that the pullback of the bundle decomposes into line bundles, and then the induced map in the cohomology mod 2 is injected. Okay, now now, for oriented bundles, we have the same the same sort of the same kind of statement, but the bundles this time will be of rank 2, not necessarily 1. Actually, all of them, except maybe one, will have rank 2, and the isomorphism will be true only on the level of rational cohomology, not in the integral cohomology. Well, let's see why this is true. Well, suppose I have suppose I have an oriented bundle. I want to split off. I want to split off one subbundle of rank 2. Okay, so suppose I have an oriented bundle of rank R, and I want to split off something of rank 2. How do I do that? something of rank 2, which would be again oriented. Then the other summand would also be oriented.
We want to split line bundles.
Well, it's not always possible. If it's not always possible to split off a line bundle, and why, by the way? Well, let's consider the complex bundle gamma of 1 over CP. I think CP1 will do. How do you split off? And let's consider it as a real vector bundle. It's real. It's oriented. Now, suppose I'm able to pull it back somewhere in such a way that the cohomology map, well, some cohomology map is injective, and the bundle splits as a sum of two oriented real bundles. What happens? Well, I use the Euler class. The Euler class of any bundle, any oriented bundle of rank 1 is 0. Why? Well, because an oriented bundle of rank 1 is trivial. So the Euler class is 0. And then this means that the Euler class of the pullback is 0, but it's in fact non-zero. It's the first Schrank class. So there are so sometimes we're not able to split a bundle into line bundles even after pulling back. So we need to use bundles of rank 2. Okay, but for rank 2 it works. Why? I want, well, I have something. I want to pull it back so that the pullback would be some plain bundle plus something. Okay, so how do I split off a plain bundle? Well, let's. Frames is. Well, let's remember what we did. What we did in the complex case. Well, in the complex case, we used flags. But here, but we could also one can obviously consider the space of flags, but the space can be constructed in several steps. Namely, the first one, step 1 is to projectivize the vector bundle itself. then we pull back, split off one segment, then we projectivize the other segment, pull back, split off another segment, and so on. So there is a similar procedure here. And in this procedure, as well as in this one, the first step is to projectivize the bundle. And what do we do for oriented bundles? Well, what is projectivization of a vector space? It's the set of all one-dimensional subspaces. So, but here we have already seen that line bundles aren't always possible. So let's take Y to be the space of oriented two planes the space of oriented two planes in E. What does this mean? Well, this means we have something which is fibered over X, but the fiber over each point is the space of oriented two planes in the fiber of V over the point. Does this make sense? Okay, so well, it's a particular case of an oriented Grassmannian. More precisely, for each X, the space of two planes is an oriented Grassmannian. Okay, now we want to know the. So basically, when I pull back, I get this splitting. Because there's the tautological vector bundle, or more precisely, tautological two-plane bundle over this thing, which will split off one oriented two-dimensional segment. But then, obviously, there's the question: why do we have an injection? Does this make any sense?
It makes some sense, yes.
So when I pull back, the tautological bundle over this space will be contained in the pullback. So I introduce a metric and a split the pullback as the tautological bundle plus something. Yes, by taking pullbacks, we get bundles of the same rank. Okay, so the question is, but there's the way did I? Hold on. Did I or did I not? Yes, I think I did. Yes. Well, it looks like everything is working, but I'm not sure. Okay. Anyway, we have this map. Why is it injective? Again, let's remember what happened when in the complex case. In the complex case, we had the Luray-Hirsch theorem, which basically told us straight away that the cohomology map is injective. Can we use this theorem in this case? Well, let's see. Let's remember why the Luray-Hirsch theorem helped us in the complex case. We did manage to prove that the cohomology of the total space is a free module over the cohomology of the base, which is quite a strong statement. We don't always have this statement for vector bundles or for fiber bundles. So if we want to apply the Luray-Hirsch theorem, we need some classes. Well, let me call them alpha 1, alpha m. In the rational cohomology of y, such that when I restrict those classes to the preimage of x, I get a basis for the cohomology of the preimage. Well, where can I get those classes? In the complex case, I took 1, and then C1 of the relative universal bundle, then C1 squared, and so on. And and what do I do now? Which classes do I take? Well, I can always take 1. And then what? Yes, so I can take the Euler class of, well, let's call it gamma. over this space there is the tautological two-plane bundle. Well, it's a two-plane bundle, and it's oriented. It has an Euler class. Well, if I have an Euler class, well, I can take it, and I can take the square of the Euler class. Etc., etc. And then up to one half the rank. Okay, now my claim is that these elements, when restricted to each fiber, generate over Q the cohomology of the fiber. So we need to be able to calculate the cohomology of the oriented Grassmannian of two planes. Well, or at least I need this for our even. Anyway, I need it rationally. So why do I have such an isomorphism?
Yeah, this E in degree 2.
Yes, where E is the Euler class of gamma. The Euler class of the universal, of the tautological two bundle. Okay, now why do I have such an isomorphism?
Space of matrices 2
yes. Well, this could help. This could help, but how?
So this is a fiber bundle with some spectral sequence.
Good thinking. So we have some spectral sequence. Okay, so okay, so we we well, first of all, let's apply the strategy. So we need to
Right, and it's also should be Q, right?
oh yeah. Okay, so let's see. So we have this. Okay, we need to calculate the cohomology of the space of two frames in R. Well, we may as well assume them orthogonal. Which is the same as the space of couples x, y, such that x and y have length 1. Well, let me say that x is orthogonal to y. R, well, R to R. Okay. Now we want to have this this answer. And basically. My claim is that the answer is the same as the spherization of the tangent space of the tangent space of the tangent bundle of the n-1 sphere. Now, is this part clear? Basically, the tangent space to the sphere as r-1 at a point is precisely the space of all elements of R which are orthogonal to this point. Okay, so now let's see. Using another spectral sequence, we will find the following answer. Oh, sorry, r minus 1, r minus 2, okay, now I have just one differential in the spectral sequence, and that's multiplication by, does anyone know by what? Well, the vibration takes x, y, x comma y to x. So here I have multiplication by the Euler class, or in fact, actually, by minus the Euler class. But anyway, it doesn't really matter because I have two groups, both of them are isomorphic to Z. So by changing a generator of one or the other, I can always change the sign of the map. So the Euler class of T as r minus 1. And so the answer is if r minus 1 is odd, then we have if r minus 1 is odd, then the Euler class is 0, and the differential is 0. So we have z in degrees r minus 2, r minus 1, to r minus 3, and if r minus 1 is even, we have z. Then the Euler characteristic is 2. The Euler class is 2. So we have z in degree 0 to r minus 3. And well, z by 2. In degree r minus 1. Which one? Yes, well, we haven't computed it yet. We've only calculated the cohomology of the space of frames, but now we need to take the quotient. Now there are two, well, yes, let's consider let's consider the two cases separately. Okay, that's something which is not quite right.
I think we can forget about torsion.
Yes, we can't forget about torsion. And, anyway, suppose I have SON, which acts on something. No, SO2, which acts on something. How do I find the cohomology of the quotient? Well, there are two ways. There's one way which is to use the spectral sequence of the map into the quotient. In this spectral sequence, we know the fiber and the total space, and we don't know the base. And with some luck, one is able to calculate it. But another way would be to use another spectral sequence for the homotopic quotient. Does anyone have an idea of what it is? The homotopic quotient. So suppose I have X, a space, sufficiently nice space. With an action of a group G. Now, well, of course, I can take the naive quotient but this naive quotient is often badly behaved. So instead, I could also take the homotopic quotient. Or another terminology is the Borel quotient, which is basically the same thing, except we multiply x by EG and take the diagonal action. Well, these two quotients have, in general, different cohomology groups, In some cases, the cohomology groups are the same. Well, to illustrate what to illustrate the difference, let's consider the case when x is a point. Then x by g is also a point. But what is the homotypic quotient? The homotypic quotient is Eg by g, which is not a point. So, but we always have a map. Basically, I take the projection to the first factor and then pass the quotients. And this map induces an isomorphism of the rational cohomology groups. If G acts with acts on X, with finite stabilizers and in a sufficiently nice way. I don't want to get into detail of what this means. Let's just say that any differentiable action of a compact group would do. In general, what one needs is a slice, and for smooth actions of compact groups, slices exist. Anyway, returning to our example, G is SO2, and we have the space of frames. Well, the space of frames the action on the space of frames is free, so it's even better than having finite stabilizers, and it's also sufficiently nice because SO2 is compact, and the action is differentiable. So there's that, and so we are able to conclude that we may as well consider the homotypic quotient instead of the naive quotient. The homology, cohomology with rational coefficients will be the same. And in this case, even with the integral coefficients, because the action is free, but not just with finite stabilizers. Well, let's Okay, let's see. So we have now we have another fiber bundle which is sometimes useful. The fiber is X. The total space is the quotient, which is what we're after, and the base is BG. Where does this fiber bundle come from? Well, it's clear that this thing maps into EG by G, which is BG, and the fiber is X. Now, in our case, X is X is something we know, and BG. So if G is SO2, BG is CP infinity. Well, let's first consider the case when R is even. R is odd, R minus 1 is even. And we consider rational coefficients. So this one lives in degree 2 R minus 3. This will be 2 R minus 2. And my claim is that this differential is non-zero. Does anyone have a suggestion as to why? This differential is non-zero. Does anyone can anyone offer an explanation why? R is odd, R minus 1 is even. Differential is not zero. Well, if it were zero, then all differentials would be zero. And so, in particular, the quotient would have cohomology in arbitrarily high degrees, which is impossible because we know that the quotient is finite dimensional. and we basically get the same answer as we wanted to get. Okay, but this is for our rod. Now, what happens for our even? Well, for our even, we
What do you face? This map induce H star triangle.
say again.
This map induces H star.
So this map induces.
I read the isomorphism.
Oh yeah, induces. Yes. Well, as I said, I don't. I can't quite read what I'm writing. This is why it's it doesn't always come out as it's supposed to. Anyway, yeah. So for our rod, the answer is easy. Now for our even, we have. We have two generators in degrees r minus 2, r minus 1. So if r is even, then r minus 1, r minus 2 is even. And we have the product to r minus 3. Okay, now, if r is even, r minus 2 is even, so this differential misses everything, and it's any differential which starts at this q goes to 0, so this thing survives. Now, what about the other one? Well, again, the other one, the other q must go to something non-zero, because otherwise all differentials would be 0, and this is impossible, because the cohomology the cohomology of a finite dimensional space must end at some point.
Why all other differentials would be
Well, there's only one chance for a differential starting at this group to be non-zero.
Why it must be?
Oh, by the way, no. I must be more careful. There is actually another option, and another option is that this group. No, I'm going too fast there. So there are two options. Well, first of all, there aren't any non-zero differentials starting here, but this one could go here, or it could go here. Which one is it? Let's think. There's probably some hints in problem sheet 3, but we don't have it. So we're on our own. There are two possibilities. Either this differential kills this element, and option 2. Option 2 is option 2 is that. Hold on. There are four rows. There are 4 rows, and the question is which one cancels with which. Is it row 1 that row 0 that cancels with row lots of rows. Well, not that many, but anyway. Q. Okay, so we have 2 odd rows, 2 even rows. Which one cancels which? Okay, I think it's the middle rows that cancel each other, and then the top row cancels the bottom row, and we basically have the same answer as in the previous case, apart from this group. No, sorry, from this group which survives. Let's see. Okay, now so this one is 0, Q, this one. Well, what's the alternative? Well, the alternative is that the alternative is the top row cancels row r minus 2, and these cancel this row cancels the bottom row. In which case we have in which case we have okay, so this is r minus 1. Where does it go? Well, it can only end up in r. Okay, so then the question is, and here we have the Euler class. So, is it true that e to the r is 0? Okay, and then so for the so basically the Euler class, and then one needs to check what happens when we restrict to the previous Grossmanian. So for the previous Grossmanian, we have e. Okay. Oh, sorry. E to the 1/2 r. Yes. So for the previous Grossmanian, we have no, for the the previous Grossmanian. What do we have? So we suppose that r is even, r minus 1 is odd. 2 r minus 4 to r minus 4, blah, 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 blah. No. Okay, 2 r minus 1 minus 3, which is 2r minus 5. Okay. So this is okay. So this is the class, and we have e to the. So for the we now consider the case when r is even, r minus 1 is odd. So to r minus 5 kills to r minus 4, which corresponds to the Euler class to the power r minus 2. Okay, so so on the one hand we have Euler class to the r minus 2. On the other hand we have sorry, r 1/2. On the other hand, we have Euler to the r minus 2. Okay, so this is 0, but we know that r minus 3 is not 0. Okay, so can we have something to the power 1/2 r 0 if something to the power r minus 3 is not 0? Well, we can have both, but only for some small values of r. Let's see which ones. So this can be true for well, this can be true. Okay, r 1/2 r is greater than r minus 3. Okay, I can solve this inequality. It's not massively difficult. Okay, I have r greater than 2r minus 6. r is less than 6, which gives me 2, 2, and 4. That's the only two. That's the only two cases where which I need to worry about. Well, if R is 2, nothing happens. We just have one oriented 2-plane in R2. So it's a point. For R equal 4, we get something. I don't know what. Well, R equal 4 is a special case. I don't have an answer. And for all other R, we have calculated the cohomology, and we proved that the middle rows cancel each other, and the top and the bottom row cancel each other, and the answer is the same as in the other case, except there is one extra generator in degree r minus 2. Okay. Now I've run over time again, but okay. Does any of what just happened make any sense whatsoever? Sure.
First one is when we take the homotopy quotient, this quotient by G means that we act G acts only on the EG part, not on the X.
No, it acts on both X and EG and on the product in the diagonal way. Because otherwise, we want this homotopy quotient to know something about the action of X on G.
Makes sense, but then this calculation, I mean, how is this mapped from homotopy quotient to the classifying space?
Well, we just take the projection from X cross EG to EG. This projection is G equivariant, so it induces a map of the quotients.
But shouldn't the phi be X quotient by G?
Well, let's see. So since okay, suppose I have X cross Y and a diagonal action. What is okay? X cross Y. So what is the fiber of this map over the orbit of some Y? The fiber is the quotient of X, but by the stabilizer of Y. But in our case, the action Y is EG, and the action is free. So the stabilizer is trivial, and I get just X.
Another question was that so when we say that e to the power of half of r is equal to 0, shouldn't it be the next degree after that?
Well, let's see. So this one lives in degree r minus 1. So this one lives in degree r. And hold on. So if this differential is non-zero, then e to 1/2 r is 0. Why? Well, because e lives here. and it lives in degree 2. And R is even, so 1/2 1/2 R is something that lives here. Okay, are there any more questions? Well, there's probably a simpler solution in problem sheet 3, and I'll try to post it somewhere, and along with last week's notes and some other notes. Okay. Are there any questions, comments, criticism, anything else we need to talk about? Well, I think we've run over time already. Anyway, so we haven't done much, but at least we have calculated the cohomology of the Grossmannian of the oriented Grossmannian G to something, at least rationally.